So imagine that you have a pot of liquid and you want to get it to boil. This liquid can be any kind of liquid. And so there are three things that you need to know to figure out how much heat you will need. And so that's what this section is going to be addressing, is what those variables are and how they affect how much heat you're going to need to add to increase that internal energy of the material in the pot. So one of the things that you need to think about, most people figure this one out pretty quickly, is that you need to know what the temperature is of the liquid. You need to know what the average kinetic energy is of that liquid already, because that will give you the starting energy of the liquid to know how much more energy you need to add, how much more heat you need to add to increase that temperature. You also need to know how much liquid is in the pot, and that should make sense, right? From what you saw in a previous video, the one with the two different size containers. So the one that was the small container with the 250 milliliters versus the one that was a 1 liter container. Those two containers are going to require different amounts of heat in order to bring them to that boiling point. So if we apply the same amount of heat to those two different size containers, the 250 milliliter container is going to boil faster because it has less material that we have to add the energy to. The last one, and this is where this can kind of apply more to some of your different fields, is the nature of the liquid. And this is even applicable to things that you do at home, and that is the nature of the liquid. So what is in the pot? What is in the container? Is it water? Is it soup? Is it some sort of, resin? That is going to make a difference on how much heat you need to add. It turns out, despite what, people have said, that old wives' tale that if you add salt to water, it makes it boil faster. That's actually not true. If you add salt to water, it actually takes longer for that water to boil because you changed the nature of the water. It's no longer water, it's water and salt, and that changes the interaction of the liquid with the heat because now you're having to move different atoms and molecules than if it was just the water. This idea applies to any material. So it doesn't matter whether we're actually talking about a liquid or if we're talking about a solid or a gas. If we're talking about any material, we still need to know these three items. So we still need to know the initial temperature of the material. We still need to know how much of that material we have. And we need to know the nature of that material. So what is it made up of? Is it all one element? Is it a mixture of elements? Is it, different compounds? What is it? So this all basically boils down to, to a concept called specific heat. So the specific heat actually is related to these different variables. So temperature change is going to be tied to this. So when we see temperature change in an equation, it is represented by delta T. So delta is the triangle for the Greek delta, and then T, so delta stands for change. So let's think about it. Which takes more heat to boil? So if you have a pot of cold water and a pot of hot water, and you put them on the stove at the same level of heat that you're going to put on, apply to them, which one's going to boil first? And it should make sense, and if you've done something like this, the hot water pot is going to boil first. And that's because that hot water pot already has a lot of internal energy, a lot of heat, and so you don't need to add a lot more in order to raise the temperature. Versus the cold water pot, where you have less internal energy, and you have to add even more energy to bring it up to the same level, the same starting level as that hot water pot. Again, there are things out there on the internet that I've come across where they say, oh no, start with a cold pot of water and it will boil faster. Nope, that's not how physics works. Physics states that the higher the temperature, the less energy, the less heat you have to apply in order to increase the temperature. The next thing is we do, like I said, need to consider the mass, so how much of the material we have, and the type of material that you have. And this is where the specific heat comes in. So we measure the type of material based on its specific heat. And specific heat is this little c when we show it in equations. And this is the amount of heat needed to increase the temperature of 1 gram of the substance, 1 degree Celsius. And if you've watched the other videos, that should sound kind of familiar. Specific heat is very similar to a calorie. Calories are just specifically for water. Specific heat applies for any material. So this value changes depending on the nature of the material. And so what we can do is we can actually use these 3 variables to determine how much heat we need to apply to a given material and a given amount of material to change its temperature. So what you've got here, Q for heat, I have no idea why it's Q. I know there are other things that H is used for, like height. So they had to assign it a letter, so they gave it Q. So heat equals the mass of the material times the specific heat, which is the amount of heat that's needed to increase 1 gram of the substance 1 degree Celsius, which for almost all substances we have determined the specific heat, and then the change in the temperature. So the change in the temperature from what we start at to what we end at, that's what that last one's going to be. And I'll show you an example of this. The C, the specific heat, is going to actually alter the amount of heat it takes to change the temperature. So the higher the C value, the higher the specific heat, the more heat it takes to change the temperature. So if you've got a really high specific heat for a material, that means it's going to take a lot of heat, a lot of energy in order to increase its temperature and likely to change its phase if you want to go from like a solid to a liquid. So let's take a look at some examples. So here we've got aluminum, copper, and gold. So these are guys that have fairly low specific heats. So you can see the C's. So we've got 0.22 for aluminum, 0.093 for copper, and 0.03 for gold. And for anybody who might work with these metals, you know, we're doing jewelry work or any sort of metal work, you probably are already familiar with the fact that these 3 metals work differently when you are applying heat to them. Gold is going to be fairly easy to heat up and melt and mold. In fact, the more pure the gold, the less heat you need. Depending on the purity of the gold, some of it can actually even be worked by the heat of your hands, just to be able to make it more flexible, to be able to mold it. The copper is going to take more energy because it's a higher temperature or a higher specific heat, and aluminum even higher. This is why we use aluminum in so many industrial type applications, because it does have that higher specific heat. It will still melt, but it takes more energy to do it. So again, I'll have another video to walk you through these problems on how to solve for the problem that's here for figuring out how much heat you have to apply to increase the temperature on this pan when it's made out of iron versus aluminum, and then which pan will warm up first, so that'll be in a separate video. The one that I wanted to have here is to show you the specific heat of different substances. Because again, many of you work in different fields, and you might be familiar with working with some of these materials by having to increase the temperature on them to alter them. So there's our copper with the 0.093. And I know some of you do glass work. So there is glass, and glass has an average of 0.16. So glass takes more heat to be able to melt and raise its temperature and melt it than something like copper. It's actually just below something like aluminum, because aluminum is at 0.22. So it takes a little more heat to be able to melt and work aluminum than it does to heat glass. So any of you who do glass work, that gives you an idea of why we use aluminum for so many different tools. And you can see some of the other ones that are here. Ice. Ice has a specific heat of 0.5, and water has a specific heat of 1. And this is why we use these materials for cooling things down or insulating things. This is also why it takes a pot of water, for example, so long to boil. All right, the last part in this video, the last topic, is thermal expansion. And what thermal expansion is, as you can see here, when the temperature of a substance is increased, those particles jiggle and move farther apart. So we talked about this in an earlier video. And so those different atoms are moving around, and depending on if we're talking about solid, liquid, or gas phase, those molecules will either be very close together or farther apart, but no matter what, they're going to start moving farther apart because they have more energy and they need to get farther apart in order to do their jiggling and rotating. And so all forms of matter generally expand when they're heated and contract when they're cooled. And so if you think about this, think about like asphalt on a street or a highway, or even concrete on a sidewalk. Those materials eventually get cracks in them. And that is because they expand in the winter or in the summer in the heat, and then they contract in the winter when it gets cold. And that contraction actually pulls, and there's not enough material, and it pulls the asphalt apart. And so we get those cracks. Water is a little odd. Water actually doesn't follow this rule. When water is liquid, it's very dense. As you can see here, the molecules hang out really closely together. When it becomes ice, they pop into these hexagonal structures. And so when water becomes ice, it expands, because it creates these open crystals. And so this is one of the exceptions. So when water is warming up, it'll expand. And when it's cooling, it will contract until it hits a specific temperature. And then at that temperature, it will then expand again until it becomes a solid. And you're familiar with this if you've ever put any sort of bottle in the freezer and then forgotten about it. You know, you put it in there to cool it off, like a water bottle or something like that, and you come back later and it's frozen and it has blown the bottle out. And that is because the water has turned into ice and it is expanded and it's pushed the bottle out because it needed more room. So just to show you what's going on, what it looks like. So here are the little water molecules. So here is the water when it's at its most dense. So it's still liquid at 4 degrees C, but the molecules are going to be close together. They're going to be shaking a little bit, but not much. And the water will be very dense at that point. If we increase the temperature, you can see the little guy gets bigger. This is because the water molecules are spreading out, because they're jiggling more, they need more space, just like we would expect any other material. When we drop the temperature, if we keep going down below 4 degrees, as we reach 0, that's when the water is going to expand again, because those molecules are popping into those crystal formations and staying in those crystal formations as a solid. All right, that's it for this section.